We're going to walk through the most common model architectures one by one. For each, I'll give you a practical explanation, including typical use cases, key strengths, and limitations. When it's helpful, I'll also drop in a quick code hint. We'll start with the simpler, more classical models, then move into deep learning, and finally touch on specialized architectures. Ready? Let's dive in. Let's start with linear regression. It's the baseline model for regression tasks, like predicting house prices or forecasting demand. Why use it? It's very fast, easy to train, and the coefficients are directly interpretable. You can also run simple diagnostics, like checking residuals, but it does come with limitations. Linear regression assumes a linear relationship between inputs and outputs, and it's sensitive to outliers and multicollinearity. Next up is logistic regression. It's commonly used for binary classification tasks where interpretable probabilities matter, things like spam detection or medical screening. Its main strengths: it's simple, produces probabilistic outputs, and is highly interpretable. But there are trade-offs. Logistic regression assumes a linear decision boundary, and it usually requires feature engineering to handle nonlinear relationships. Now, let's talk about support vector machines, or SVMs. They're often used for text classification and are especially effective on small to medium-sized, high-dimensional problems. The strengths of SVMs: they work really well in high-dimensional spaces and are flexible thanks to the use of kernels. But here's the catch. SVMs don't scale well to very large data sets, and they require careful tuning of the kernel and parameters to get good results. Next, let's look at decision trees. They're great when you need interpretability or rule-based decisions, for example, credit approval rules or simple medical diagnosis trees. Their strengths: they're easy to interpret, handle both categorical and numerical features, and require very little pre-processing. But they do have limitations. Decision trees can have high variance, meaning they tend to overfit, and they're sensitive to small changes in the data. Now, let's move on to random forests. They're a reliable baseline for tabular data, often used in tasks like fraud detection or churn prediction. Their strengths: random forests are robust, less prone to overfitting than a single decision tree, and they make it easy to check feature importance. But there are trade-offs. They're less interpretable than a single tree and tend to use more memory and computation. Next up, let's talk about gradient boosting machines, including XGBoost, LightGBM, and CatBoost. They're widely used for tabular data when you need state-of-the-art performance, like in Kaggle competitions, credit scoring, or risk modeling. Their strengths: they deliver exceptional performance on structured data, handle heterogeneous features, and specialized libraries bring extra benefits. For example, LightGBM is optimized for speed, and CatBoost handles categorical data automatically. But there are some downsides. These models are sensitive to hyperparameters, take longer to tune, and can overfit if not properly regularized. Now, let's look at K-nearest neighbors, or KNN. It's often used for simple classification or regression baselines, recommendation systems based on similarity, and works best with small data sets. The strengths: KNN is simple, requires no training time since it's a lazy learner, and it's quite flexible. However, it has its limitations. KNN can be slow at prediction time because it compares each new query to all training points. It also performs poorly on high-dimensional data. That's the curse of dimensionality, and it requires feature scaling for good results. Now let's talk about clustering algorithms, specifically K-means and DeepScan. They're commonly used for customer segmentation, anomaly detection, image color quantization with K-means, and spatial cluster detection with DeepScan. Here's how they differ. K-means is fast and efficient, but it requires you to predefine the number of clusters and assumes they have a roughly spherical shape. DBSCAN, on the other hand, can find clusters of arbitrary shapes and automatically detect outliers, but it needs carefully tuned density parameters and can struggle when cluster densities vary. Let's talk about the multilayer perceptron, often called an MLP or a feed-forward neural network. Think of it as the reliable workhorse of the neural network world. Where does it shine? If you have tabular data with hidden nonlinear patterns, or you need to approximate a complex function, the MLP is a fantastic starting point. It's also incredibly flexible and serves as a simple, essential component in larger, more sophisticated AI models. But every tool has its limits. Ask an MLP to process a high-resolution image, and it quickly becomes inefficient. That's the specialized job of a CNN. Another challenge is the number of dials you have to tune. Getting an MLP to perform its best means carefully adjusting many different hyperparameters. Let's dive into convolutional neural networks, or CNNs. If you've ever seen a computer identify a cat in a photo or a self-driving car detect a pedestrian, you've seen CNNs in action. They're the engine behind most image tasks, from sorting your photos to pinpointing objects with systems like YOLO, to outlining the precise shape of every object in a medical scan with a UNet. So, what makes them so good? CNNs are brilliantly designed for images. They're incredibly efficient. They learn features in a logical hierarchy, and for a long time, they were the undisputed state of the art. But they do have their challenges. They're often data hungry, needing thousands of labeled examples. Their architecture, which is so good at seeing local patterns like edges, can struggle to understand the global context of an image. This is exactly why new models like vision transformers have emerged. And of course, building deeper and more powerful CNNs comes with a significant computational cost. Imagine you're trying to predict the next word in a sentence or the next note in a song. You need a model with a memory. This is exactly what recurrent neural networks, RNNs, LSTMs, and GRUs were built for. They were the go-to solution for any sequential data, from forecasting stock prices and transcribing speech to building the first powerful language models. Their architecture is inherently designed for order and can flexibly handle sequences of any length, which is a huge advantage. But that sequential processing is also their biggest weakness. It makes them slow to train, and their memory is surprisingly short-sighted, often forgetting crucial information from much earlier in the sequence. This fundamental limitation in capturing long-range context is why transformers have now become the dominant architecture for most advanced NLP work. If we had to point to one model that defines the current era of AI, it would be the transformer. It started a revolution in natural language processing, mastering tasks like translation and summarization, and then gave us the powerful large language models we see today. But its ambition didn't stop there. Transformers have successfully crossed over into other domains, redefining computer vision with the Vision Transformer, VIT, and tackling audio and complex multimodal challenges. So, what's the secret to its success? The self-attention mechanism gives it a global understanding from the start, allowing it to see connections between words or pixels, no matter how far apart they are. And because it processes the entire sequence at once, it's perfectly built for parallel computing, supercharging its training speed. The catch? That powerful self-attention has a steep computational price. As sequences get longer, the resource requirements grow at a quadratic rate, which can be prohibitive. In short, transformers are incredibly powerful, but they are also incredibly hungry for compute and data. Let's explore autoencoders and variational autoencoders, or VAEs. Think of them as neural networks that learn the essence of your data. What can you do with them? They're great for compressing data and learning its fundamental features. They can also act as anomaly detectors. Because they learn to reconstruct normal data perfectly, anything weird or anomalous will have a high reconstruction error. And VAEs take it a step further. They can generate completely new data samples. So how do they work? They force the network to learn a compact, bottleneck representation of the input. The VAE's special trick is that it learns a smooth, continuous latent space, which is what allows it to generate new samples. Now for the caveats. If you compare a VAE's generated image to one from a GAN, the VAEs might look a bit blurry. This is a known trade-off. Also, a key distinction is that only VAEs are true probabilistic models. A standard autoencoder is just a compressor without a built-in understanding of probability. Imagine a forger and an art critic locked in a constant battle, each pushing the other to become better. That's the core idea behind generative adversarial networks, or GANs. They are the artists of the AI world, famous for generating stunningly high-quality, photorealistic images. But they can do more than just create faces. They can transform photos into paintings with CycleGAN, enhance image resolution, and create synthetic data for augmentation. Their masterpiece is their output. The images they produce are incredibly sharp and convincing. The adversarial process is a brilliant, flexible concept that drives this quality. However, this artistic genius is notoriously temperamental. Training GANs is like managing a fragile rivalry. It's often unstable and can easily fall apart. They sometimes get stuck producing the same few images, a problem known as mode collapse, and they require a delicate touch to tune, being very sensitive to their settings. What if your data isn't a neat spreadsheet, but a web of connections, like a social network or the interactions between atoms in a molecule? This is the world of graph neural networks, or GNNs. They're the tool of choice for tasks where relationships are the star of the show. They can predict the properties of a new molecule, recommend a friend on social media, or spot a coordinated fraud scheme by analyzing the connections between entities. The magic of a GNN is that it doesn't just look at individual points, it lets nodes communicate with their neighbors. This allows it to learn directly from the complex, interconnected structure of the data. The trade-off is that this power comes with complexity. Training on massive graphs requires clever sampling to be feasible. There's also a Goldilocks problem with depth. Too many layers, and all the nodes start to look the same, a problem called oversmoothing. They also require a more thoughtful approach to batching data compared to standard neural networks. Imagine teaching a child to play a new game without ever telling them the rules. You just give them a thumbs up for good moves and a thumbs down for bad ones. That's the essence of reinforcement learning, or RL. It's the engine behind robots learning to walk, AI that masters complex games like Go and Dota, and systems that manage resources in data centers. In short, it's for building agents that learn to make a sequence of decisions on their own. Its superpower is tackling problems where there's no instruction manual, there are no labeled data sets. The agent learns purely from its own experience and a reward signal. But this power comes with major hurdles. RL is incredibly data hungry. Getting the reward signal right is more of an art than a science. The training process can be unpredictable, and these instabilities make it a risky endeavor for real-world applications where safety is paramount. Here are a few practical tips that apply across machine learning architectures. Tip number 1, start simple. Begin with a baseline model like linear regression, logistic regression, or a decision tree before moving on to deep learning models. Tip number 2, feature engineering still matters. It's especially crucial for traditional models. Deep neural networks can reduce the need, but they don't replace the value of clean, well-structured data. Tip number 3, use regularization and early stopping. Techniques like L1, L2, dropout, and early stopping help prevent overfitting and improve generalization. Tip number 4, don't forget scaling. Standardize or normalize your inputs, especially for distance-based models like KNN and SVM, as well as for many neural networks. Tip number 5, keep explainability in mind. When transparency is important, simpler models are often better. For black box models, use tools like SHAP or LIME to interpret predictions.